In the last video we looked at rotational kinematics and the analogs with translational kinematics. Now we're going to look at the analogs of force and inertia, which are going to be called torque and rotational inertia. So if you're trying to open a door and you have a choice between pushing, this is a bird's eye view of a door looking down, not that you would ever have that view because there would be a wall in the way, but anyway, looking down on a door, and you want to open that door by exerting a force on it. If you had a choice between exerting a force here near the hinge versus over here by the handle far away from the hinge, and you imagine which one of those is going to be more effective for easily opening the door, some experience might tell you that this one here is going to be more effective. So this is different from what we're used to. We can imagine these forces being exactly the same magnitude, but we're going to get different effects. So the location of the force relative to the axis of rotation, which in this case is the hinge, now makes a difference. And you can see this in everyday situations. A tire iron here trying to get the lug nuts off of this tire. They tend to be pretty long rather than a nice short little wrench cut off here or something. And the reason for that is you can get more torque, is what we're going to call this force that causes things to rotate. And if that's not working for you, if the lug nut is stuck, what people sometimes do is they slide a pipe. Can't really see that black on that picture, but anyway, slide a pipe over that tire iron to give you a greater distance from the axis of rotation. This distance from the axis of rotation here, RA or RB, is known as the lever arm. So if you get a larger lever arm, you're going to be able to get more torque to rotate that object. That's why pipe wrenches tend to be quite long. It gives you quite a bit of torque. Now, it's not only the location of the force, but the angle of the force also matters. So start out looking at this picture over here. Don't get distracted by these down here. If we imagine the same force being applied to the same location on the door, but now at different angles, which of these is going to be most effective? Obviously, this guy is not going to do anything, and you might know by experience that this is less effective as well. And this, again, will be the most effective way. You're going to get the largest torque by pushing in a direction perpendicular to the, that's not a very good perpendicular sign there, perpendicular to the axis of rotation. So if you're not pushing perpendicular, we can still analyze the amount of torque. By the way, the torque is going to be a symbol tau right here, so T-O-R-Q-U-E. There we have it. And it's just the product of the force times the lever arm, with this little exception here that if your force is not perpendicular, you have two choices. You can, well, we'll start over here because this is kind of more straightforward. If I've got this force at an angle here, then I just need the perpendicular component of the force times the lever arm, and that will give me the torque. If the force is just perpendicular like this one was, you can just multiply that force times the lever arm and you're good to go. Another way of doing it, which isn't quite as intuitive, but occasionally it's more useful, is taking the entire force, not a component of it, and if you extend a line out and then draw a line from your axis of rotation to that line coming off your force vector such that you get a perpendicular angle here, and then you take that distance here, so you could call that the perpendicular distance times the force. And if your force is going, say, in this direction here, you would extend that line backwards, and this would be your perpendicular distance here. But either way, it's going to work out to be the same. You're still going to end up with sine or cosine of the angle depending on how you're defining theta. So that gives you the torque on an object. Now you can have more than one force acting on an object, in which case you would just consider the net torque due to those different forces and the locations where they're acting. So here's a quick little example. We have two wheels nested on each other, and there is a rotation axis through the center of both of those wheels. We've got 50 Newton forces acting at different locations, and this one is at an angle. So we're going to find the sum of the torques is going to be Since these are going in opposite directions, well, they're going to tend to make it rotate in opposite directions. Then we need to subtract these. So we can say the torque from B minus the torque, it's not a tau, minus the torque from A. The torque from B is going to be the force of B times the lever arm, which is RB. And then we're going to have, I want just the perpendicular component, so that's going to be a cosine of 30 in there, minus the torque from A, which is the force of A times the lever arm of A. And this one is perpendicular. You could put in a cosine of 0, but that's just going to be 1. So there is your equation. If you go ahead and plug in numbers, you're going to have 50 for this force. The lever arm of B is 50 centimeters, so 0.5 meters, times cosine of 30, minus same 50 Newton force, but a different lever arm here. This one is only 30 centimeters, or 0.3. This works out to be about 21.65. This works out to be exactly 15. So this works out to be 6.65. Oh, we haven't talked about units yet. So you've got a distance times a force. So that's going to be meters times newtons. We don't write Newton meters because we don't want to confuse this with joules, because torques are not energies. So we just swap the place and make them meter newtons. In imperial units, you might have heard of foot-pounds. So same idea, a distance times a force, foot-pounds of torque. They talk about that with trucks and things like that. All right, now that is the analog of force is torque, but what about the other side of Newton's second law, F equals ma? Well, if we consider a force acting on a single particle on the edge of a disk, and that particle is the distance r from the axis of rotation, if I multiply both sides by r here, I'm going to have F times r. That's going to be force times my lever arm, r times ma. This is going to give me torque. And then if I want rotational stuff instead of linear stuff, then acceleration is r alpha from the last unit. That's how you convert between linear and angular acceleration. And so we can combine those r's and we get this expression, torque equals mr squared alpha. Okay, now that is for a single particle. And so if we want to know the sum of the torques, it's going to be the sum of the inertias of all the particles times alpha. So this term here, the sum of the masses times their distances, and they might be a bunch of different distances throughout this disk. This is called the moment of inertia, or just rotational inertia, and the symbol for it is I. I don't know why. That's an ugly summation symbol there, so we can do a little better. Ooh, it just is ugly. But anyway, this term here is known as the rotational inertia. So we can rewrite our sum of the torques equals I alpha, which is essentially our rotational version of Newton's second law. And as you might have guessed, eventually we'll replace this with an integral later on, because these r's might be different, or they will be different for the different particles at different locations. And so for now, I'll just give you the list of these moments of inertia, for some different shapes. If you have a thin hoop, it just works out to be mr squared. Now this is rotating about an axis through its middle. If you take that same hoop and you rotate it around through the edge, so it's like standing up now, then you get this other funky expression here. A solid disk will look like this. You get a factor of 1/2 in there, and so forth. So you get these different moments of inertia. But the point is that now the distribution of mass matters. If we imagine that we have a disk and a cylinder, or basically two different cylinders, it's just a flatter, wider cylinder, right? And if these have the exact same mass, they're both mass m, but here the mass is distributed further away from the axis of rotation, then this is going to have more resistance to rotation, what we typically call inertia, right? So the moment of inertia of this guy is going to be larger than the moment of inertia of that guy. So it gets a little more complicated, but we can handle that, right? Okay, here is an example that looks deceptively simple, but it's actually a little tricky. Anyway, we've got two blocks hanging from a pulley, so something like this. That's my pulley, here's my rope, magically not touching the pulley. And we have a larger block, 10 kilograms over here, and then a smaller 3 kilogram block. This is apparently a less dense material. So anyway, if we want to know the acceleration of these blocks, and we also have our pulley is 1 kilogram, and it has a radius of 20 centimeters, or 0.2 meters. And now we're going to take into account the rotational inertia of this pulley when we find the acceleration of the blocks. First of all, let's do a quick calculation ignoring the pulley like we would have done before, just to get a ballpark estimate of what the acceleration would be if this were a massless, frictionless pulley. And then we would imagine that if we take the inertia of the pulley into account, we should get something a bit less than the acceleration ignoring the pulley. So ignoring the pulley, we can just do F equals ma for the entire system. So on the system, you're going to have gravity on this guy minus gravity on that guy. Let's go ahead and call this block A and block B. So you'd have gravity on A minus gravity on B would equal the sum of the mass of the system, so mass of A plus mass of B. And we could solve for acceleration this way. So acceleration, this is going to be 10 minus 3, if you factor out a 9.8, divided by 10 plus 3. So the acceleration would work out to be approximately 5.28 meters per second squared. Okay, now if we want to factor in the pulley and the rotational inertia, we can't just use F equals ma because this thing is rotating. So how do we exactly factor in the mass of a rotating system? So we have to use torque equals I alpha, and we're going to use sum of the torques equals I alpha. And since this is a pulley, we're going to assume it's a disk. And the moment of inertia for a disk, if you don't remember, you can come back over here and say, okay, there's a disk, it's rotating about its center. So 1/2 mr squared is the moment of inertia of a disk. So we'll keep that over here, mr squared. Now the torques acting on this disk, be careful to not assume that it's just gravity on both of these. So I'm going to run through that real quick and show how ridiculous an answer you get. So if I say the sum of my torques is gravity on A minus gravity on B times the lever arm, R, and I set that equal to I alpha, where I is 1/2 m, I'm going to put mp for mass of pulley, times r squared, times alpha. Now alpha is A over R, so we can go ahead and put that in, and kind of nicely this cancels one of those r's, that cancels the other. So we're going to get this expression here. But if I went ahead and plugged in these numbers, this is going to be 10 minus 3 times 9.8 equals 1/2 times the mass of the pulley, which is just 1, times acceleration. So you're going to have 7 times 9.8 times 2, and you get an acceleration of 137.2 meters per second squared, which is obviously ridiculous because this is much faster than the acceleration of free fall. So this is not how you want to do it. And you might suspect just by looking at this that we didn't really take into account the inertia of these two blocks, right? We considered the forces due to them, but we only took into account really the inertia of the pulley. And the reason why this is wrong is because if you think about the forces acting on this block here, you've got gravity down, gravity on A, and then you have some tension pulling back up, and that tension has got to be smaller than gravity such that this block will accelerate downwards. And it's that tension that is, let's make our disk a little bigger here, it's that tension that's being exerted on the side of the disk. So our actual equation for torque needs to be the tension from A minus the tension from B. And these ropes are both equidistant from the center of that disc, so we can just multiply by the radius of the disc. That's our lever arm. So essentially this is the torque. Don't get confused with my T's and my tau's. Sorry about that. So the torque from A is tension times the lever arm. Torque from B is tension times the lever arm. This is going to equal 1/2 mass of pulley times R squared. And we can go ahead and make that same substitution of A over R and make our R's go away. So that all works out nice. Now I don't know the tensions directly, so I can use force information to figure out equations for these tensions and then come back and plug them in. So I'm going to jump over here. For block A, you're going to have gravity on A, so we're just doing net force equals MA. Right? Okay, so gravity on A minus the tension on A equals the mass of A times the acceleration. So if I solve this for tension on A, I'm going to get gravity on A minus its mass times its acceleration. And then we're going to do the same thing for block B. So on block B, just so that I have the same signs on my accelerations, I'm going to do the larger force minus the smaller force. And this one's accelerating upwards, so we're going to have tension on B minus gravity on B equals mass of B times the acceleration. These accelerations are going to be the same because this rope is not going to get loose. So we can assume that all these accelerations are the same. The acceleration of the blocks, acceleration of the rope, and the tangential acceleration of the disc, because it moves with the rope. We're assuming it's not sliding here. So that's why we can just leave one acceleration through all of these things. Alright, so solve this guy for tension on B. You're going to have mass of B acceleration plus gravity on B. Now I can plug all this in up here. So gravity on A minus mass of A times acceleration. That thing minus mass of B acceleration plus gravity on B. In parentheses, don't forget to distribute all that stuff. Okay, so this whole thing is equal to 1/2 mass of pulley times acceleration. Draw a line here just so we don't get confused. Alright, and this is really the physics of it. Now we just have to plug in numbers and we can solve for acceleration. If we want to factor some things out, we can. So I'm going to have gravity of A minus gravity of B when I distribute that. So that is going to be 10 minus 3 times 9.8. So those are my gravities. And then I'm going to have minus mass of A, I'm going to write it this way, plus mass of B times acceleration. So I'm just kind of collecting terms here. Equals 1/2 mass of pulley times acceleration. Now I've got another acceleration here, so I'm going to move this all over to that side. Might as well call this 7 times 9.8. This is going to end up being added, and then we can factor out an A again. So we're going to have mass of A plus mass of B plus 1/2 the mass of the pulley. So essentially we get what we had over here, right? We're going to have 7 times 9.8 divided by 13, only we have to factor in the mass of the pulley, but it doesn't factor in completely. It's only half the mass of the pulley that factors in, so it's going to divide by something a little bit larger. The mass of the pulley is 1, so we're going to have 7 times 9.8 divided by 13.5, which is pretty close to what we had here, right? But dividing by a slightly larger number, which is going to make our acceleration slightly less, which is what we're expecting. 5.08 meters per second squared. There, we did it. Welcome to rotational mechanics. See you next time.